Thank you very much. Like we've heard with the two presenters before us, polymer concrete has varying physical properties as well as attributes, and fire resistance is not one of them. Polymer concrete originally came to North America as a material that you filled holes and potholes in concrete on highways and bridges. In the last 30 years, 30, 40, 50 years actually, it has developed into engineers understanding or discovering that they could use it for various products, non-structural, various products and applications where it has superior performance to regular Portland cement concrete or other mixed designs. And in fact, there's several uses out there of where it has replaced UHPC as a joint filler and closure pore application. What I'm going to do is I'm just going to go through some applications. This one right here? Yes. I'm going to go through some different application. This is non-scientific. This is real world. This is where polymer concrete's been used and used successfully and continues to be used. The first one is polymer concrete is used as a mortar or a grout. And that can be a grout with just a neat filler or with small filler aggregate into it to give it some body and reduce resin content. It's polymer concrete, patching material, or closure pores, or joints, things like that. And then the last thing that we're going to talk about is, that precast polymer concrete. That's taking polymer concrete, different types of resins, with different types of fillers, and making a finished product, construction product. And the last thing we're going to talk about is polymer materials for sealing concrete cracks and surfaces. And that right now is probably the fastest growing area that we're speaking of with the transportation infrastructure and the condition it's in. They're using polymer materials to buy time on the life of these structures, the service life. And polymer materials have been widely accepted to do that. Okay. I think some of this project that you see right here was actually shown in some of the earlier pictures. This was a project where there were hundreds, if not thousands, of precast concrete panels that were set on structural steel diaphragms, and they came back in after a large section of panels were set, and they installed polymer concrete in between the joints. Testing was done years ago at the University of New Mexico with Dr. Taha to prove the shear strength, pull-out strength, and lap splice development length of the polymer concrete, because these joints are all connected and they need to be structurally connected after the polymer concrete is applied. Found out that it actually is superior to Portland cement concrete and ultra-high performance concrete. So that's why they chose to use polymer concrete. In this case, it was a methyl methacrylate polymer concrete for these closure pores. This is another use. There's a big problem with beam ends, the deterioration of beam ends on precast concrete bridge elements. And they're caused at bridge piers, where the water comes down through the joints, lays on top of the joints, splashes onto the precast concrete element, causes deterioration. What you see here is they're coming in, they're cleaning off a deteriorated concrete beam end, forming it up to make sure that they get the polymer concrete where they want it and a sufficient thickness that they want. Simple pouring. They're pouring it out of a 5-gallon bucket. And this is the completed repair. You see, this is not a huge bridge, but beam ends are a critical problem in the country. Not only concrete beam ends, but steel beam ends. So this is a way of fixing a concrete beam end. This is another interesting project. This was a very high elevated bridge pier. And what you see is there was deterioration again, a joint leaking down on top of the bridge pier, causing deterioration. And this is a scary amount of deterioration right here. I mean, you right on the border of that bearing pad's not doing anything, or it could fail at any moment. They didn't really know what to do, and I think if you went in there with standard Portland cement concrete, it wouldn't perform. It wouldn't bond, and it wouldn't stay there. It would eventually just spall right back off again. So what they did is they decided to use polymer concrete. This was also, when they finished it, they turned it into a seismic retrofit project. So they formed up these piers. You can see right here the formwork. They poured the polymer concrete in there, vibrated it. This polymer concrete had 50% aggregate extension added to it. That was a 3/8 pea gravel aggregate. Still had sufficient flow to come down the depth of that, and that's about a 10-foot to 12-foot depth from the top of the pour to the bottom of those forms. Removed the forms, and after the fact, they came in and they put in steel bands to enhance the seismic retrofit. This was a very unique application. This is another one. Polymer concrete has been used for a long time for bridge bearing pads, especially by the railroad. Railroads really like it because they can come in and jack up a bridge bearing, form it up, well, first of all, demo it, form up the pad, pour the polymer concrete, set the bridge down, and let the trains run across it. And trains usually are on a very tight schedule. You know, the funny statement is, which came first, God or the railroad? And the railroad would tell you they came first, okay? So you don't mess around with the railroad. Well, this is simply, they didn't even jack the bridge up. They just demoed out the loose concrete, Portland cement concrete, formed it up, again, poured it with 5-gallon buckets, a little vibrator to get the material to flow underneath the bearing pad, and then stripped down the forms. And this is, you can see over here, this is polymer concrete right here. And right in here. Nice thing about it is it has tremendous flow. The slump is very, very high. This is a project that happened probably 25 or 30 years ago in Washington, D.C. This bridge was a problem, and what they did is they came in and they put a new deck on top of the bridge, but it was a non-composite precast bridge deck. So each one of the panels sat down on these steel plates that were designed to slide between those two steel plates. So the bridge was actually moving back and forth on the structural steel. The Nelson studs were what were used, these Nelson studs were what was used to interlock or connect the precast bridge panels to the structural steel, or the bearing pad in this case. What they did is they formed 3 holes. They put a funnel to create a head on the polymer concrete. They poured the material down through the bridge deck, the precast deck panel, and waited for it to come up the 2 sight holes on the sides to determine that they had filled the entire project. And you can see this is the bridge there. I guess, I don't know how many years ago, they actually knocked this bridge down and built a brand new lift bridge, which is, they went from 3 lanes wide to it's 6 lane wide in each direction now. A statement was made, and I'm not correcting anybody, but this is very unique. The equipment hasn't been developed yet for polymer concrete. This is a project on a beltway, or a loop, as they call it, outside of London, or in London, England. And they have a problem where every joint on the highway is dissimilar. And what they do is they get tremendous clickety, 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 click as the cars go down the highway, and the neighbors are right behind that wall on the right-hand picture there. So it's huge public complaints. So they put together a project. It's a 5-year project. I think this highway is about 50 miles long. They're coming through, and at every joint, they're milling it down 2 inches by about 12 inches, and they're pouring polymer concrete not only on the joints, but also around every manhole or any kind of cut into the main roadway. I think I have a picture right here. If you can look, this right over here is a continuous mixing machine. What they're doing is they're mixing about 6 cubic yards of polymer concrete out of that truck. They have 3 trucks on the job site, so as one empties, they pull the second one in, they go load the first one. Then they're pouring it into a bobcat that has a side discharge, and they just run down these joints. Okay, let me go back a second here. Back. So far, everything has worked fantastic. It's wonderful. They have 3 other beltways, so to speak, in the London area where they have a very similar situation. As with us in the United States, their problem over there is money, not projects and a need. So we'll see how that goes further in the future. This is a installation of a different type of polymer concrete. It's a thin polymer concrete overlay. And it's designed that you put it down in a slurry, you gauge rake it out, you see gauge rakes here, then you use a spike roller to spike it nice and level, and then you broadcast on the right-hand side over there, you will see you broadcast a wear-resistant aggregate into the surface. In this case, it was a calcined bauxite, which has very high wear resistance for the finished surface. You're looking at a thickness here of 3/8 or less, 3/8 of an inch or less for the total installation. And one thing that's nice is this is a lift deck, so weight is very important. Our greatest fear was what was going to happen is when this thing came up, that the polymer concrete was just going to slide off of it like a sheet. That was not the case. So what you have is you have a steel polymer primer, polymer concrete, and then the addition of the wear-resistant aggregate on the surface. This is that project. This is kind of what it looks like before you put the aggregate on, and this is with the aggregate on, and that's the project down there. This is just outside of Manhattan in New York. Okay, polymers, not polymer concrete, but this actually could be polymer concrete because it's got aggregate mixed in with the whole system, but it's really a polymer membrane. It's the application of, you can see a spray application of a polymer-based material. It's a waterproofing membrane, very high elongation, in excess of 300% elongation. And that's really important on a concrete bridge deck, because if you have cracks in the bridge deck and it's going through thermal cycling, it's going through load cycling, 300% elongation is the only way you're going to prevent those cracks from reappearing and getting moisture into them and further deterioration of the bridge deck. So what you do is you spray 2 coats, around 90 mils per coat. You broadcast aggregate onto the surface after you're done, and you have a riding surface similar to the polymer overlay, the slurry that I just showed you, but this is a pure resin. This is applicable for steel or concrete bridge decks. This can be spray applied, or it can also, on smaller bridges, it can be hand applied. And it has application in parking structures also. This is an airport application. I had the opportunity, I guess the fortune to do this job. This is Newark Airport. We did it in March. It was freezing cold. It was the main runway at Newark Airport, and what they did is they installed the center line runway lights. The runway cans, they're about 12, 18 inches in diameter, but they saw cut all the way through the runway. So what happened is, after time, that saw cut space settled. And the pilots were refusing to land on this runway because it was right in line with the front landing gear. So we went out there, they demoed the top 2 inches, they came in and they poured polymer concrete and finished it, and they came back at a later time to put the light cans back in. And this was an hour and a half later. We had about 10 engineers standing out there with hammers tapping on the polymer concrete, and the minute they tapped on it and it sounded hard, they got on the radio, and a plane took off over our heads. So it's pretty exciting. And the whole while that we're working on this, our total protection was 2 Port Authority, New York pickup trucks parked diagonally, or parked nose to nose with each other across the runway. So thankfully, no planes landed on top of us. This is another very unique application. This is in the northern part of Canada. This is a huge electrical power transmission line project where they're actually going through permafrost to set anchor bolts. The temperatures, they bring this stuff in on ice road trucks during the wintertime, and they've actually gotten a little late in the season. They've flown material in on helicopters. These rods are going down into the ground 20 and 30 feet through permafrost to get down below the permafrost. They're mixing up the polymer concrete, just pouring it down in the holes, vibrating it just a little bit, and you can see on the side over there, trying to do a little bit of QC in the field, but that's very difficult to do. So it's very effective for anchor bolt grouts, as I said earlier. This is a little more QC. Very small batches. We actually have to make it in we send them 0.62 gallons, 50 pounds of powder, and they mix it in the field, and that's just enough. I think 2 of those mixes or 3 of those mixes actually fill up 1 anchor bolt hole. Temperatures are down to minus 40 degrees Fahrenheit. At that point, it's Fahrenheit, Celsius. It doesn't really matter. Okay. This is precast products, as I said earlier. People are finding more and more applications for polymer concrete. As we learned so far today, it's not applicable to everything. If you have a fire problem, if there's chances of creep being an issue, polymer concrete is not your answer. But in precast, there are applications for polymer concrete. This is a bridge where they decided to come in and replace the entire bridge barrier with a steel barrier on top of it. What was unique about this is they used these panels, which are precast. They're 10 feet long, and they can be in any shape. They could be a single slope, they can be a jersey shape, they can be an F shape, any height. We've made them anywhere from 56 inches tall to 32 inches tall. What was unique about this is in upstate New York, and when they plow their bridges, what their plow drivers do is they come up with the plow, they turn the wheel until the plow hits the barrier, and they just let the barrier guide them across the bridge. Well, if you look right down here, this is cast with a piece of granite underneath it. So when they're hitting what they think is the barrier, they're hitting that piece of granite, and that's guiding them across the bridge. The other thing unique here is, it's not real visible in this picture, I'm sorry, but this is a little indentation in the panel, and it's a all-weather retroreflective stripe. Because it's vertical, unless there's 3.5 feet of snow, it's not going to get covered up with snow. It's not going to get covered up with rain and lose retroreflectivity. So that's the nice thing about precasting these things. You can do anything with them, anything at all. But the big important thing on this was it was a stay-in-place form. They formed up the back. They used these on the front as a stay-in-place form, saved a lot of time, a lot of labor. These are 2 more applications. These are tunnel applications. And you can see this panel right here, I think it was 56 or 58 inches tall. They set it against the wall. These are all electrical conduit ducts running through here. They use these, again, as stay-in-place forms. These had, in this case, they had a white stripe on one side of the tunnel, on one direction, and a yellow stripe on the other direction in that tunnel. On the right-hand side, that's a tunnel in New York City. They came in and they replaced. They had a really bad problem with the air ducts were collapsing with the tiles, and from what I understand, tiles in tunnels right now are only European supplied, and the labor to put them in has disappeared. They can't find laborers that actually can install tunnel tiles. So this was a heaven sent I drove through the Fort McHenry Tunnel, and I kept looking at it going, this is a polymer concrete project. But you can see they cast in the air flues, and they cast in the steps to get you up to the crossovers or the man walkway. Again, another thing that's important in a tunnel is whiteness, bright whiteness. The surface of the polymer concrete does not attract, it's not like Portland cement concrete where it has porosity and roughness to it. This is like a sheet of plastic. So when you go in there, you can clean it with simple cleaning chemicals and wash trucks, brush trucks. The white panels enhance safety inside the tunnel because they enhance the lights in the tunnel and make it brighter for the traveling public. 2 more minutes. Okay, I'm going to burn through this stuff now. This is just a test panel. You can see the tiles were falling off the wall. These are lightweight panels. They have a hollow core cast into them with 1/4 of an inch of polymer concrete on each side. This panel is 12 feet long. 2 men could pick it up and carry it. And it's bolted to the wall with a space behind it. So if the wall does leak, it goes down the back of the panel and comes out underneath the panel. You can use it as a concrete median barrier or a toll plaza. We had a big issue with cars running up the wrong side of a toll plaza. In the Northeast, you never know what's going to happen. And this is, I'll go through this real quick. This is other polymer-based materials. These are methacrylate materials and hydroelectric methacrylate for sealing bridge decks, cracks and porosity in bridge decks. Simple application. Mix the material up, you spread it down. By gravity, it seeps down into the pores and the cracks in the concrete, and then you put a coat of sand on the top for friction for the traffic. It's used on piers. This is down in New Orleans. It's a U.S. Corps of Engineers pier down in New Orleans. This was done after the last hurricane down there. It's been formulated for epoxy injection. We can do epoxy injection with this, with something as simple as a 2-component caulking gun. It's got a viscosity just a little bit higher than water. So it goes wherever you want it to go. Sometimes it goes where you don't want it to go. But it's very effective for sealing, for injecting cracks. And the other thing is, this is the state of New Jersey. They have a tremendous problem with the salt contamination from years of plowing snow off the side of the road, where their bridge abutments are all cracking because they're contaminated with salt. So what they wanted to do is just get 2 to 5 years out of it, and they went in and they coated a vertical surface with the high molecular weight methacrylate to seal off the surface so that they wouldn't get further deterioration from road salts and moisture. So as summary, polymer concrete has high strength, compressive, flexural, elongation, low temperature applications, down to -40 Fahrenheit or C, rapid cure, an hour or less in most cases. It's waterproof, has no freeze-thaw deterioration. You can run it through as many freeze-thaw cycles as you want. It's not going to deteriorate. Precast polymer concrete, if you can come up with a shape, forms can be made to make that shape. They're lightweight. You can make panels that are half the thickness that you would of concrete, so they're much lighter than concrete. They're, again, waterproof, and they can be used for new construction or retrofit of or rehabilitation of existing structures. Polymer concrete materials, crack sealers for surface porosity, permanent, they will not degrade. Some of the materials that we use for treating are basically hydrophobic. What they're doing is they're making the water beat up on the surface and roll off the deck. Well, what happens is with traffic, taking that water that's got some of the chemical that's treating the deck, it pounds it into the deck, emulsifies what you've treated the deck with, and eventually the cars run it off the bridge deck. Horizontal, vertical, and overhead applications, and low pressure injection possibilities. Any questions?
You have a few minutes, but first, in order.
Yes.